Hello, my name is Virginia Weston, and in this lab I will be showing how I experimentally recorded data of a falling object and created two different computer models of the system. So one of the main goals of this lab was to predict motion in the y direction when the net force of a falling object is not constant, and to do that we used Newton's second law, also known as the momentum principle, which says that the net force is equal to the change in momentum over the change in time, and we're able to derive the velocity update equation from the momentum principle, and we also use the update position formula throughout our GlowScript programs. We also analyzed our experimental data through Tracker and compared that data to two different models that consider only gravity, which would be the net force is equal to the force of gravity, and another model which considers gravity and drag force, which would be the net force equal to the force of gravity plus the drag force. To set up this lab, I used a scrunchie that has a mass of 0.0567 kilograms, which is about 2 ounces. Here is the experimental setup that was in Tracker. The origin was set at the object's initial position so that the scrunchie was following in the negative y direction. My phone was propped upright so the orientation did not need to be changed, and the calibration stick was calibrated to a known height of 1.7 meters. The initial velocity was considered to be 0 since it was dropped from rest, and the frame rate of the video was 30 frames per second. The position graph from Tracker has a curve in its slope which demonstrates that there is not a constant net force. The initial positions were taken from time equals 0 seconds, which were experimentally obtained. The scrunchie's initial position was obtained from Tracker's initial position data from the previous slide. The initial velocity with the drag force constant was set to 0 because we are neglecting drag. The net force was set equal to only the weight force, which is m times g, and those values are specified in the script. The velocity update and position formulas were derived from the momentum principle, aka Newton's second law, and these values were ran through a loop in the program. Here is a visual from GlowScript of the predicted position versus time in the form of a graph and a model. To find the constant for drag force B, I plugged in values that got me closer to the final position of the scrunchie and Tracker. The value of B that I found was 0.0019. The script differs from the previous script because the net force with drag is equal to the weight force plus the drag force. The formula to compute the drag force is equal to the constant B times the magnitude of the velocity squared times j hat because the force is only in the y direction. The graph of the right is the velocity versus time graph of the computer model considering drag force. There are some slight differences. The model with drag is supposed to curve and straighten out towards the end, which can be barely seen between 0.45 and 0.5 seconds. The model with drag is more accurate for terminal velocity than the one only considering gravity. In this case, however, the scrunchie was not dropped and analyzed long enough for it to have reached its true terminal velocity, and that's why there's not many changes in the graph that considers drag versus the one that only considers the weight force. Terminal velocity happens when the force of drag pointing up equals the force of gravity pointing down, which means that the net force in the y direction is 0. So what if our object was initially thrown downwards? The graph on the right depicts an object thrown with an initial velocity of -2 meters per second. With a non-zero initial velocity, the magnitude of the velocity of the graph on the right is the same as the graph on the left, which is the velocity versus time graph considering drag from an initial velocity of 0 meters per second. But the graph on the right should reach its terminal velocity sooner than the graph on the left. Now let's look at all of our data graphed on top of each other. The green dots represent the experimental position data that was obtained from Tracker by establishing the center of mass of the scrunchie for each video frame. The orange data is the first GlowScript model that is only considering weight and the net force, and the pink data is the GlowScript model whose net force is equal to the weight force plus the drag force. As you can see, the general shape of all the trend lines had the same curve. The orange model without drag overestimated where the scrunchie's final position would be. The pink curve considered the drag force in its final position is closer to the experimental data's. The reason why there are discrepancies in the position versus time data could be because it was hard to determine where exactly the center of mass was in Tracker because the frames were blurry. To fix this, I could use a camera with higher frames per second. There also could be discrepancies due to some minimal movement in the x direction and other forces that were not considered in this lab. We also did not completely reach terminal velocity in this lab. In this lab, we established that falling objects move with non-zero net force in the y direction. To make our computational models of motion more accurate, we can consider drag force in the y direction, but it's still going to be an imperfect model because the net force considers other forces that exist naturally. In our computational models, we consistently use Newton's second law and g as the acceleration due to gravity. And finally, terminal velocity happens when the drag force pointing up has exactly the balanced force of gravity that's pointing down, which means that the net force is 0. Thank you for watching.